Boa tarde. Então, voltamos agora para o mini curso número 3, com o professor Uri Ascher. Essa é a terceira das 4 aulas. Please, Professor Ascher.
Obrigado. So this is the third talk out of 4 that I'm giving as part of my short course weeks. And as I mentioned before, I try to make each of these lectures self-contained, but somehow connected to others. And so this one in particular will continue the last example of data completion that I discussed last Thursday, but there will be no data completion. It's just that the example or the application that I discussed is the same, but without data completion. Specifically, this would lead us to discussing the estimation of the trace of a large implicit matrix. And the applications would be related to what those of us who have been here last Thursday have seen then. Then next Thursday, on 2 days from now, I'll switch gears and talk about something that relates to the first talk, but in a bit of a different, quite a bit of a different sense. And in that talk, I will examine the relationship of the community that most people here belong to with visual computing, i.e. computer graphics and image processing. So there's a list of papers, starting with a paper with Kees van den Doel, where we looked at the piecewise constant solutions and tried to take advantage of knowing this by using level set methods. And we devised algorithms that had an adaptive nature and a stochastic nature for that particular setting, and came up with some algorithm that sort of will be contained in what I say now. Then Fred Rusta, who was at that time still in the beginning stages of his studies, was a research PhD by this time, and we had also level set methods, but also in this paper we already talked about more general situation, and we analyzed where we need the stochastic nature of the algorithms and so on. From here, there was this data completion paper that I mentioned last time, but that is not mentioned here. And Fred really went on to consider the question of implicit matrix trace estimation that I will discuss. And from that followed more of an uncertainty quantification kind of arguments. And that is a final paper that we wrote on in a more review-ish, philosophical sort of way. So I'm going to sort of build on these papers in a sequence of some sort, except that I will start in the middle with this one here. This is Fred. And he's now an assistant professor in the University of Queensland in Brisbane. And this is the program. And now let me start right away with the estimation of the trace of an implicit matrix. So for the first, I don't know, 15 or so minutes, we're going to forget about inverse problems. And let's do something else for just a while. And so a purely algebraic problem, but I would like to introduce a class of algorithms that lots of people are interested in fact, called randomized algorithms. So you introduce randomization, okay, into your algorithms in order to gain some advantage. sort of not the usual thought, not an immediately usual thought, let's put it this way. But again, there is a big community that does exactly that, usually associated with computer science. So we have a matrix A, which is S by S. S is large, or else it makes no sense to look at this. And it is symmetric, positive, semi-definite. Okay? And we are assuming that A is given only implicitly. There's a black box. I can send a vector to the black box, and out comes A times that vector. But I do not have the matrix A. And so if I had the matrix A, then then I would not know how to spend 15 minutes on the problem, because the trace of a matrix is, of course, nothing but the sum of the diagonal elements. But I don't have the diagonal elements, because the matrix is given only implicitly. Now, why would this ever come in applications? As a matter of fact, it's not even difficult to come up with an example of such a matrix. If you think of a matrix, if the matrix A is something like an inverse of some matrix, inverse is difficult. It's a PDE inversion, yeah? Times a matrix. Let's call it, I don't know, some matrix. Okay, it can be, in fact, like that as well. Now, let's make it square, okay, but still. That means that in order to calculate A, I have to solve C inverse of each columns of this matrix big J. But now, if all I want is A times a vector, I can write here times a vector, V, and then I do J times V, which is simple, obtain another vector, and now I have only one inversion to do. So it makes sense to look at this. And in fact, this work describes a process in numerical linear algebra, really. But again, one that has this randomization in it. So what we can do is the following. We write that the trace of A is equal to the trace of some B transpose B. In fact, Samuli has already introduced SVD, but I can write a symmetric positive semi-definite matrix as U transpose the eigenvalues, diagonal matrix here, times U, and so I can choose B to be the square roots of the eigenvalues times U. Okay, so there are lots of B's actually for a given A. So I can write it in this way, and now the trace of B transpose B is well known to be the Frobenius norm of B squared, and I can look instead at the expectation of the 2 norm of BW, where W is drawn from a probability distribution that satisfies this scaling condition, and obtain that the trace is the expectation of W transpose AW. And so now I can approximate the expectation. And so Monte Carlo approximation, draw n W's and calculate WJ transpose the AW and average them. And if I can get away with n being much smaller than S, then I win. That makes sense. If you say, oh, let n be S, then I have once again nothing to say. Because if you allow me to choose S vectors in doing that, I will choose the identity matrix, and here it is, the matrix A discovered. but so with S samples, I can choose them such that A is in my hand. But we want to get away with S, n, little n, being much smaller than the size of the matrix S. So now the question is, which probability distribution are you going to use? And I'm going to suggest 3 possibilities here. The normal distribution, I will call it Gaussian. The Rademacher distribution, which is a special case of Bernoulli. Basically, we are going to choose W's that have components that are either 1 or -1. -1 at probability half. okay, equal probability for 1 or minus 1. And the random subset is the same unit matrix, but now you choose at random a subset of the unit vectors. Kind of simpler idea, but not necessarily better, just simpler. And the selling features of Hutchinson, which is why it's called Hutchinson and not Rademacher, is that he showed that using this Rademacher distribution, you get a smaller variance than when you use the normal distribution. And that's important because you're going to stop basically by some sort of a, you're going to choose your n and stop and report the result. It's nice that the variance is smaller. The nice thing about this random subset is that you don't even have to have a symmetric positive semi-definite. So the conditions for it to work are more relaxed. And it also is, not surprisingly, somewhat slower than the other two. I don't know, those of you who've been in last Thursday, but of course last Thursday was a long time ago, I did show you numbers with this random subset idea. So there was a paper by Avron and Toledo that was a starting point. And basically what we did, when I say we, I mean Fred, actually, in this case. What we did was to improve their bounds, but of similar bounds. And the first thing we have to get used to, if you haven't seen it before, is what is the purpose? Okay, so let me write it down here so that we won't forget it. So usually you have some sort of a stopping criterion, and in this case, let's say that it is relative. So you want the approximate, let's call it trace n of a. Our approximation, we want it minus the exact, divided by the exact, absolute value divided by exact. You want it to be less than or equal than epsilon, right? So this is the same as writing that the absolute value here is less than or equal than the trace of A. Right. But now we are in probability land. There's no reason to assume that you need it exactly when everything is approximate and statistically correct only. So now you want that the probability of this thing be less than or equal than greater than or equal than 1 minus delta, where delta is a small number. So you want it to be reasonably close to 1, but not 1. Maybe delta is 0.1. So you're happy with the 0.9 probability that this holds. So the idea of looking at such a bound is maybe new to most people in the inverse problem community, but it is not new at all in the randomized algorithms community. And Aklioptas wrote a paper using this, which is related to what we are doing, but the idea of looking at this is much older than, I mean, he also has previous references as well. By the way, this guy worked for Google, sort of industrial researcher. Aklioptas. And so that's what we are going to look at. We're going to try to find what is the n, what kind of value of n can we get away with such that given epsilon and delta, this will hold, the probabilistic bound. And so, here I'm going to write this thing down as well so that it will not disappear. Let's define C of epsilon delta to be 1 over epsilon square times the log of 1 over 2 delta, 2 over delta, what is it? 2 over delta. Like that. This constant comes in everywhere, especially the annoying feature of 1 over epsilon square here. And then you get results of this sort, that using Gaussian probability distribution, the bound, the probabilistic bound is this guy. Yeah? And this will hold if your n is over 8 times c. And if you're using Hutchinson, then that 8 reduces to 6. Okay, so again, these are cleanups of results of other people, but there are better results obtained actually very neatly, if I may say so. Of course, so now we are practical people and we want to assess what does this result say. Okay. So if epsilon is 10 to the power 8, if epsilon is at 10 to the power minus 8, like we do when we write a paper about how fast conjugate gradient method converges, then see here, now you have bounds here that say that if you take n to be more than 10 to the power 17, things will work. Haha. Who cares? Yeah. But the whole point here is to use epsilon and delta, which are not so small. For example, 0.1. Okay. So if it's 0.1, then you have here maybe 1,000. So so these bounds will say that if you sample 1,000 times, you already get some idea of what the result is, even if the matrix size is 100 million, I think that somebody said only a while ago, okay? Regardless of the size of the matrix. So that's not so obvious, I would say. No, I shouldn't say that. That's not so intuitive. Regardless of the size of the matrix, regardless of what is inside the matrix, other than the fact that it is symmetric, positive, semi-definite. So there's power. That's actually well known, that there is power to Monte Carlo methods if you are not looking for high accuracy. For high accuracy, they sort of not so great, but for rough accuracy, they can perform miracles, such as in multidimensional integration. You are not allowed to look at a matrix A. It's a black box, but you can wonder, you are allowed to wonder what properties it has, because maybe it comes from a family of matrices, yeah. So suppose now we look at the properties and we can define kappa G, G is for Gaussian, to be the norm of A over the trace of A. And if that guy is small, then we have a better bound. Okay, so for example, if the matrix is diagonal, then the norm, when I have norm without anything, it's the least squares norm. So the norm here is the largest eigenvalue. The trace is the sum of the eigenvalues. Okay, so if the sum of the eigenvalues is significantly larger than the largest one, then you have a better bound here. With Hutchinson, it's even stronger in a sense for diagonal matrices, because for Hutchinson, we have a kappa H with something similar here. 2 and 8 are the same as far as we are concerned with this sort of rough estimates. Yeah. But still, then if you look at the sum of off-diagonal elements squared divided by the diagonal, corresponding diagonal element and the maximum of those, yeah, then for diagonal matrix, that will be 0. And so for Hutchinson, one shot will do it. Stronger result. And if it is almost diagonal, then you're also better off with Hutchinson in a significant way. Here's these are 2 more theorems in our paper, but I will concentrate on the essence, really. And again, the same C comes in all of them, I should say. Okay, for the random subset, once again, a random subset of the unit of vectors of the unit matrix. Then you have to look at the distances between what does it mean? It means W transpose AW, where W is a unit vector. You are actually catching exactly one of the elements of the main diagonal. Now, if they're all equal, then you got it. But if they're not equal, then you could be very far away in approximating the sum of these guys. So this is what it says, but more, much longer proof than what I just said. You look at the distance here and maximize the distance times S divided by the trace. And then you get a bound like that. And if you if you draw and then remember what you drew and you don't draw it again, then you get it even better. But that's of no interest for this quick lecture. Okay. We are still, we haven't mentioned inverse problems yet, by the way. And here is what, yeah. So one conclusion that I want you to keep in mind, this random subset is good only if the other two cannot be used. If and only if. No, I shouldn't say that. There are situations where they cannot be used, and then it's important to remember it because it may be used. And I showed you an example on Thursday. If you need to do data completion in order for the other two to work, in that example that I showed last Thursday, for those who were here last Thursday, the random subset did not need any data completion. And I showed you examples where if the data completion was good enough, then Gauss and Hutchinson, I think it was Gaussian that I showed, were better than the random subset. But if you need to do too much data completion, then the random subset still works, whereas the other two give you bad results. So we don't want to forget that. It's another tool in our toolbox. But generally, let's consider the first two, okay? But we don't want to forget this random subset for a rainy day. Yeah. Here's an example, simple example. So A here is vector x times x transpose, rank 1 matrix. Everybody sees this? So x looks like this. So it's 1 e to the power minus theta, or theta is a parameter, e to the minus 2 theta. Like that. And we look at this vector times its transpose, so a matrix, and then just divided by the norm in order to scale it. And so the trace is 1. The rank is 1, okay, and you can see that the Gaussian, so basically a few hundreds experiments were done, and this is the average, and you can see that the Gaussian doesn't care what is the size of theta, but Hutchinson does care, because for Hutchinson, at some point when theta begins to be kind of close to 1 and even more than 1, then these guys go down very quickly, and so XX transpose, what's away from the diagonal is that times this, e to the minus 4, you need the square of these guys. And so they are small compared to the diagonal elements, and in fact, you see the bound showing up when theta is large enough for these to be, the one to be dominant compared to the rest. And then the random subset, if theta is 1, then this is a vector of 1s, and you're going to get all the AI are the same. And so in one iteration, it does it. Example where random subset is better than Gaussian. But when theta gets small, the magic is gone, and it shoots up and becomes worse right away. We are still with linear algebra, by the way. Randomized algorithm. And for some reason, this paper of ours received the largest number of citations to date compared to the others. Maybe because the catchment area of the audience has been wider. Yeah. Any questions? What? OK, so now we want to continue and eventually get back to we want to get back to inverse problems. What should we work with? Hutchinson, which has a smaller variance and has a nicer conditions that I showed you, or maybe Gaussian. Why would you want Gaussian? We want Gaussian because we want also necessary bounds, not only sufficient. Okay, and we want to somehow try to trap the right kind of in from below and not only from above. And here, the theory that we have works for Gaussian and not for Hutchinson. It's just maybe with enough theory, one would want to stick with Hutchinson. We don't have that theory, unfortunately, so we continue with Gaussian. The fortunate thing is with the application that we've been looking at, that's okay to do. It's not much worse, really, if at all. And also the rank of the matrices that we look at, because we are looking at, scarce data or sparse data, continuing from the previous talk, then that helps as well, the Gaussian distribution. OK. So goodbye to Hutchinson. Let's stick with the Gaussian distribution. And let's move on. I'm going to leave the implicit matrix trace estimation at this part of the table and move to this part of the table and start a new subject for a few more minutes. And then I'll try to connect them. I want to ask sort of philosophical questions regarding what do we mean by a stopping criterion. I tried to do that also in a previous talk, lecture last week, but I want to come back to it. So if you look at just about any code that MATLAB has, my favorite example is ODEs, initial value ODEs. So there's a code called ODE45. I don't know how many people here have used it just to solve ODEs. Okay. So if you, as a user, tell MATLAB to just solve it, then it will basically figure out, it doesn't figure out, sorry, it takes some tolerances. The absolute tolerance is 10 to the minus 6, and the relative tolerance is 10 to the minus 3, if you want to know. Why would you want to know that? I don't know, but it is true. And then it tries to come up to satisfy some error tolerance. Okay, sorry, error criterion. So the error tolerance I just told you, and there is an error estimate of some sort, and the code will stop when this has been achieved, the estimation of the error in some sense. But is raw really given? And in fact, I've already answered in some sense, because most practitioners don't have any idea of what their raw should be. I mean, and so they let MATLAB do the choosing for them. Only in some special circumstances you want to insist on more accuracy, and MATLAB allows you to do that. Okay, but the vast majority of users for ODEs will just say, don't ask me about tolerances, just solve the problem already. So the raw is not really seriously given, and so this work opens a sort of different point of view that numerical analysts really, I mean, they think it's a sacrilege. You have to have a raw, you have to have an error criterion to stop the iteration. But in fact, when you look at what MATLAB does, like everybody else, the ODE45, the error estimation there, it doesn't estimate the error of the global error of your actual solution. It really estimates only locally the error and decides on the step size based on that as you go along. Right? So in fact, MATLAB can deliver to you, ODE45 can deliver a completely wrong solution. Definitely possible. I have many examples to show you with this can happen. Because it doesn't really, I mean, the error criterion that will say the solution has got to be within 10 to the power minus 3 or whatever, that's too expensive. Okay. So they don't do that unless a special procedure is started. Okay. So it does make sense to look at in the correct context, it does make sense to look at probabilistic error criteria. You're not really losing anything compared to practice. Now I'm back to inverse problems, and I would like to introduce my notation that unfortunately is not the same as other speakers here. So I will call the observed data D, okay, D for data, and assume that there are L of them. okay? And then we are looking for M, okay? And M would be some distributed function, conductivity, structure, or whatever, permeability, and so on and so forth. And the AF is a forward operator, and the forward operator delivers prediction of what the data should be given M. And then the question is, find M such that the predicted data agrees with the observed data up to noise. We further consider a PDE case where there is a source, okay, and you have a linear differential operator. It's linear not in M, it's linear in U, the field which is the solution of the differential equation. And so we write here the discrete Green's function for that linear operator. And so the field U is G times the source. Okay? And it depends on M, the unknown for the inverse problem. And so the forward operator consists of projecting the field to the locations where the data has been measured. Okay, so we're looking at the same location of the data, and therefore we compare the result of this PGQ to the observed data D. An example that I showed again, that I showed before, I'm going to show it again. So this is a geophysical experiment, and the objective of the inverse problem is to find these three boxes, okay, in the sand, buried in the sand. This is geophysics, so, and therefore this is 10 kilometers, this is 4 kilometers, big box, okay? And the measurements are given only on this loop, so it's definitely scarce or sparse data, okay? Not on the entire domain. Okay, but there are three of them. In fact, the measurements are for three different frequencies. Let's not talk about that. And the equations that we are trying to that we are using for the forward model is the Maxwell's equations in the domain where they have lots of damping. And we look at it in the frequency domain in this particular case. It's not so important. Okay, so we all know that by now, that if we assume nice assumptions about the noise, namely in the measurements of D, namely that it's a zero mean and that the covariance is actually, the covariance matrix is identity times a scalar, sigma square, then in fact it makes sense to look at the data misfit function as the least squares norm of the difference between the predicted and the observed data squared. And then the Morozov discrepancy principle tells you that you want to reduce phi of M until it is less than or equal than rho, where rho is sigma squared times L, the number of data in D. So here we have a criterion and the tolerance, rho. I mean, assuming that you somehow know sigma, and assuming that the noise really is in this idealized distribution. But life is much harder. And in fact, the thing that we are after is the accuracy of the M that we compute compared to some idealized exact solution, not phi of M. Phi of M is what we have, not what we want. Okay? And in particular, in this example, the phi of M is the difference between this and this. In this geophysical, it's not so large. It's actually quite small, but the recovery, this is supposed to be the boxes, and these are different depths. Yeah. And that's not anywhere near the three boxes. I mean, at least we got the three signs that the three boxes are there. Okay, that's already a great result in mining engineering. So you see that the difference in the M minus M star are significantly larger than phi at our best solution. Okay? I don't want to say don't look at phi of m by any means. It's not only that we have it, it's also that it makes sense to do it because what you're doing is reducing phi of m until you begin to fit noise, and you don't want to fit noise. There's a very good reason to do that. But again, it doesn't deliver to you a solution m that is close to the, that is necessarily close. Otherwise there would be no exploration geophysics. Yeah, so there are a few things to do because the results are not so great in the end. Okay, the point is, in general, that in fact rho is violated immediately. People stop before they actually get to the level of rho. For instance, factor of 1.5 rho is what we have used, and others as well. And what the people, okay, so here's a general slide that I will show once and not discuss much more. And again, I'm taking Samuli for opening the topic for me, in fact, here. So if you do Tikhonov type regularization, where R of m is a prior, I would say, and beta is a constant, if you try to solve this minimization problem, then you take the gradient, right, and equate to 0. Now, you can look instead at a constraint formulation. You want to minimize phi of m such that R of m is less than or equal than some tau. And when you want the necessary condition for this, you form the Lagrangian. Everybody with me, Lagrangian? And take the gradient and compare it equate to 0. And what comes out is the same thing, except that there's a tau here instead of a beta and so on. Okay, so, but the necessary conditions look similar. Okay, and you can also look at the third formulation where you minimize R subject to phi of m less than or equal to our friend rho. It comes from Moses. And again, when you take the gradient and equate to 0, you get something similar to solve. So these are three formulations. This is well known, and it is used mostly when you use L1 norm, in fact, instead of L2, and it's called lasso and so on. There's lots of literature on that. I just want to mention it in passing because in the context here, we know rho, we do not know tau and beta. So one of these formulations, actually, we have a better idea of what the error tolerance constant should be than the other two. So in fact, each of these has some advantage over the others. This one has the advantage that we have an idea of what rho should be. This one has the advantage in the L1 context because the constraints here are simple. They are box constraints. They're simple to use, to solve. So people often move from this rho to this tau using Pareto curve. There's a paper by Friedlander and Ewout, his first name is, Vandenberg, where they do exactly this, in fact. And this here, that's what machine learning people like because they are used to probability. And so this is the prior, and beta basically says how strongly do we believe in the prior, or maybe how strongly we don't believe in the data in some sense, yeah? So that has an immediate interpretation for them, whereas the other ones are a bit of magic. So each of those, in fact, has some advantages. Now let's make it more complicated, in case it's not complicated yet, and have a few data sets. And that is the usual mode of operation in geophysics, in fact. I've listed here several applications, but the first three are the ones that I'm used to. Seismic data inversion in oil exploration. Many more experts and much more attention has been devoted to this problem, and so, in fact, some of the ideas came from there. But also in this electromagnetic data inversion, I've already shown you this paper from 2004, where we already had several data sets, and direct current resistivity that I will use as examples here. It's a classical example. Again, I showed it already, but maybe even those who haven't been with me last Thursday will have seen this. So we want to find out if there is oil in the Gulf of Mexico without having it blow up one day and cause a disaster. And the question is, what were they doing there in the first place? And the answer is they looked at this, and found that it's a good idea to dig in the middle of the bay. So somebody actually found that there is oil there. And this is the classical sort of schematic experiment. I don't want to trivialize it too much. So you have a boat, and it has a tail like this, and it has guns here that make explosions, and you have receivers here that record the sound. And so based on the sound waves, the data would be the sine waves, and you want to reconstruct to see if under the seabed there is some action of interest. So of course, there are multiple data, and here the data really are in the millions, if not more. Just the data sets. So, here's another one, EIT. This is, I just took it from the web. I doubt that people use this. Actually, I'm pretty sure it's not true. But this is from, I don't know, 10 or 15 years. But this guy is wearing a frightening belt with electrodes. And what they do is they turn off some of them and on some of them. And by turning off and on different ones, generate different experiments. It's good for demonstration, for illustration, I would say. And this is a result of such an experiment, a picture of the lung. Not a very sharp one, really. I just downloaded this from the web a while back. So in our notation, we have here S data sets. S has to do something with the matrix. S data sets. And DI, D1 all the way to DS. And each one corresponds to a source QI, Okay? So Fi of M would be the same projection of UI, which is the solution of the PDE for source QI. And this comes with noise eta I. And so the whole problem is just a duplication of what we saw before, S times. So if we assume that all the noises are of the same have the same covariance matrix, not a trivial assumption, then phi of m, the best objective function here would be just the sum of the least squares differences between the predicted and the observed data. Now we can write the Fi's as as columns of a matrix big F, and the Di as the columns of the matrix D, big D. And then the 2 norm becomes a Frobenius norm. Basically, sum up all the squares. And then the maximum a posteriori merit function would be to have here this add to phi m beta times R of m, where R of m is the prior. Okay, so this is the a posteriori would be incorporating the data. We are going to eventually use an implicit R of m instead of an explicit one. I will get to that later. And again, we seek to reduce the merit function to the noise level times 1.5, in fact. And so once again, we have here the discrepancy principle, except that the rho is now sigma square Ls times S. And, but the question is this a reasonable criterion? And the answer is like before. It has some significant reasons not to take it too seriously. It's just the best we can do. It doesn't mean it's good. And so if you look at an example of a PDE, so we're looking for a mu of x. We have sources qi, we have solutions ui, And so the Green's function will be this. We discretize this, and the Green's function will be the inverse of that G of M. Yeah. And M is related to mu by a pointwise function that takes into account. We actually use it in order to introduce bounds on mu. You often know bounds on mu in practice, and that's why it's called mu and not M up in this slide here. Okay. And again, I'm repeating myself from last Thursday, but let me do it anyway. So we're going to look at a square domain, and we're going to measure data here and here. I mean, not data, but yeah, like data here and here. And here we're going to have locations for sources that each source is a delta function here minus a delta function here, or here minus here, and so on. So all combinations of those, each combination of those, this corresponds to that funny belt that guy had in the picture with the electrodes turned off and on. Okay. So we can generate more and less data and compare. And here it is. So this is actually using total variation in addition to something else that I will describe. And it turns out if you do it with 49 right-hand sides, then you get this terrible picture. This is the true model is here, and this is not very good, but this is very good already. It's a difficult problem because it is diffusive, so this is really a very good result. And you can see that it's the same thing that was done here, but the result is much better when you have more data. So we really do want large S. However, large S means very expensive because this is like, I will call this 4,000, by the way. This is 4,000, much easier to say. So if I want to evaluate phi of m, the difference between the exact the observed data and the predicted data, 4,000 PDE solves. I mean, that's a lot. Okay, so we want a smaller price to pay. So here comes the first topic about implicit trace estimation. Comes back. Because now we're going to define, so before here, where was it? Here I said I have an A, here is B. Now I say here is B. Here is B. The B is not just something that comes out of A, it is big F minus big D. And now A is B transpose B. So it's symmetric positive semi-definite, and in fact it is only semi-definite because the data, remember, it was only on a loop, in example, in a 3-dimension thing. So it, again, like in the previous talk, we have matrices that have more rows than columns. Okay, so we have that phi of m, the thing that we are trying to calculate, is in fact the Frobenius norm of this matrix B, right? And that is equal to the trace of A, and that will be the expected value of the norm of BW square, where W again is drawn from a scaled distribution. Then we apply Monte Carlo exactly as before, and that gives us an unbiased estimator of phi of m that costs, hopefully, only n PDE solves instead of S. So if S is 4,000, if n is 10, then we are ahead. Yeah. Let n be 10, but of course we have to make sure that it has enough quality, the approximation. So what we have here specifically is this big F. The cost of phi comes from big F, not from big D. Yeah, the forward solver. And what do you have here? You have BW. BW means BWJ. Yeah. So BWJ means I have to look at the sum of F times the WI, the component of the vector WJ. And then I can write this, in this case, because of linearity and because the matrix big P is constant. Then I can write it as F based on a weighted average of the sources. So it's a new source, if you wish, which is the weighted average of the previous ones. So indeed, there are only going to be in such Fs. Okay. So in such PDE solutions, just to calculate an approximation for the misfit function. So of course, the next question is, how large should n be? We would like it to be as small as possible. That really determines how expensive the whole operation will be. Sometimes it's pretty large. Again, I think I told you in one of the lectures last time that there were big plans to put some huge computer centers in Brazil, in fact, for calculations like that, for calculations like this. So, the larger n, the better, yeah. But that brings again the question of how important it is to satisfy some error tolerance, some error criterion, because you're paying a lot for that. So here, it is natural to satisfy our stopping criterion only in a probability range. Basically, we are turning into this probabilistic error criterion. Okay. We are going to assume that we know rho, just to make everything else simpler. Then we are going to discuss what we mean by that, by knowing it. So now we're going to do a stochastic model reduction, i.e. add those W's there. And that's the menu for this item of the outline. Let's talk first about model reduction and implicit matrix trace estimation. Is everybody more or less with me still? Questions?
I have a question. How do you generate? So my question is basically, how do you generate these samples in the previous case for the trace? Do you use some kind of Metropolis hastings or something like that? Or
no, some of the arguments remind of Metropolis, and the plot that I showed had to do with a number of rejections and acceptances. Yeah, but the vectors W themselves, you just draw it from Gaussian distribution. You just draw it. In MATLAB, you use rand n.
Yeah. But basically, my question was, if you didn't have the Gaussian distribution,
yeah,
how would you do it?
That's right. Yeah. Then you would have to.
For the Gaussian, I don't have a question. Yeah.
So your question is very good, but we basically get away from it because we are using Gaussian distribution. In general, you would use MCMC for sampling. MCS in Monte Carlo, Markov chain Monte Carlo, yeah, in order to sample for some sort of a general given probability. I don't want to go there.
Okay.
discretize the space, you have an ODE, and you want to reduce the dimension of that ODE.
Yeah.
How is it related to this?
Right. So model reduction is a very large topic, and I don't want to suggest that what I'm doing now is the only thing that can be done in order to do model reduction. Not at all, not at all. But so it's kind of hard to answer this question because all I'm showing is the sort of model reduction that we do here. Let me show it to you and come back if it makes sense. Please ask it again. Remember, phi of m has SPD solves. And so I keep on showing the same slide with little changes as they come along, because that sort of puts together the parts of this lecture. That's the idea. So, so here suddenly we say, wait a minute, phi of m is not some m. It is m sub k. We have iterations. We start with m sub 0, a guess for what this solution of the inverse problem is, and we iterate m1, m2. Everything is nonlinear here, by the way, except for the problem for u. Yeah. So, so in general, we have an iterate m sub k, and we want to get the next one. So, so it's phi hat of m s sub k. Okay, and I will write it as, and now at the iteration k, I've decided to use w s sub k, s sub k random vectors. Okay, so I can put them in a matrix W, and the matrix W will have S rows and S sub k columns. S sub k better be much smaller than S, or else we are not doing anything. Yeah. So I can write what I wrote before, that was B times Wj. We can write as, so this is B, and now write all the Wj's together. That will be the matrix W, big W, okay, written here. It's the same notation exactly. Sorry, it's the same thing, but written in slightly different notation. Meant to be more suggestive in the application context. Right, so the point is that, again, I think this is the last time I show the same slide here. But there is a little difference. And the point is that before we had little n, and we asked how large n should be, and now I'm saying that this little n is S sub k, right, in the kth iteration. Okay. So we use this general randomized algorithm for linear algebra in the context of our inverse problem. The size S sub k depends on the iteration, by the way. It's not the same size for we actually adaptively change it. I will show how. Now comes, in case you're too awake, here is something that makes you even more sleepy, I'm afraid. So let me go through it quickly. Okay, refined theory. And for refined theory, we're going to look at the gamma distribution, which is essentially least normal distribution several times, and there is one problem with this. There's one problem with this, and that is that that it is two-sided. We want one-sided bound. We want to look at it one-sided. Okay? And this is what's written here. So if the approximation of the trace is, let's say, smaller than this, and so the absolute value will make that like so, and then in that case, you would have that sort of expression, right? And in the other situation, you would have this sort of expression. Okay, so two one-sided, which are equivalent to this two-sided expression. None of this is, by the way, it's not rocket science, but it's a lot of detail, and so that's why I just want to move on through them. And it turns out that there's a theorem here that Fred and Gabor Zekeli proved that says that a sufficient condition is as follows, that there is an n0 such that the probability of this chi-squared variable normalized that is less than 1 minus epsilon is less than or equal than delta. And in that case, also, this sort of one-sided bound holds. Okay, and correspondingly, there's another sufficient condition for the other side of this, okay, that says that the same thing, but the n sub 0 is, really should be more than epsilon to the power minus 2. So this 1 over epsilon square does not go away. Yeah? Again, there is an n such that this holds, and that means that this holds. The difference between this and the previous ones, the main difference is that we also have necessary condition. Namely, that if this holds, then necessarily for all n greater than n sub 0, you have this sort of description. And the difference between here and here is that here it's n and here it's n times r, where r is the rank of A. And you have a similar result also in the previous, in the next theorem. Again, the only thing you want to look at is the n sub 0 compared to nr. And the point is that if the rank of the matrix goes small, then the necessary and sufficient conditions sort of get closer to each other. And then you have a better quantification of what that n should be. So sparse data, scarce data sometimes helps you in this sense. And so we're getting close to an algorithm. Now I have to introduce a method that I have not introduced yet. So we have an iterate m sub k, and we want the next guy. And so we have to calculate a correction vector, delta mk. And we are going to multiply it by some gamma k. And we are going to use, for delta mk, we're going to use a stabilized Gauss-Newton method. So this is just and so what we're going to do, in fact, I'm going to show this to you in detail in a moment, but this is sort of an overview. First, we're going to use a stabilized Gauss-Newton, and secondly, we are going to apply a limited number of inner preconditioned conjugate gradient iterations instead of a Tikhonov-type regularization. And it's called, I'll mention that in a moment. So if we have only one data set, which allows us to write things more clearly, then our objective is to reduce this phi of m, which is, again, the predicted minus the observed data. And so we take the Jacobian matrix of this f of m, and that's called the sensitivity matrix. Okay, sensitivity matrix. And then Gauss-Newton solves at each iteration a linearized least squares problem. Okay, and so the normal equations for these linearized least squares problems is J transpose J times delta m is equal to minus the gradient of phi of m, and then you're supposed to add that to mk and obtain mk plus 1. The problem here is that the matrix J has more columns than rows, right? And if it has more columns than rows, the J transpose J is singular. Okay. Not only that, not only is it singular, but also this f of m contains GMQ. Remember, GMQ means solve one PDE system. But if you take the derivative with respect to m, then you're going to have instead of q, you're going to have a matrix here. So that's like here. So you really don't want that. It's going to cost you a lot to just calculate the Jacobian. So you want a method that never calculates a Jacobian. You only want to have Jacobian times vectors, and conjugate gradient, of course, comes to mind. Okay. But now we say conjugate gradient, we are going to use it, but it is still singular. But the conjugate gradient method has this property that, first of all, it hits the large eigenvectors, eigenvalues, and only then the smaller ones. And so you can apply conjugate gradient methods even if the system is singular, but don't go all the way, stop somewhere. Okay, that is Hansen's important work from, I think it was his PhD thesis, in fact. And this is called, he called it iterative regularization. And because he was doing linear problems. Non-linear problems, I don't know anything which is not iterative, so I don't like this name. So I'm going to call it dynamic regularization, okay? As a distinction. Reader, his name is Reader, right? This is, Reader did some work, theoretical work on this dynamical regularization in the nonlinear context. But a big question that we had, which is when do you stop it? So you take a few conjugate gradient iterations, how many? We actually came up with algorithms which are different from those of Reader. And so now when we have many data sets, we are going to do more to the Gauss-Newton method. That is the next thing. I want to stop once again and ask if there are questions here. This method, by the way, I knew about Reader, but I gave a lot of happy talks on this over the years. And some people told me that in the oil industry, they've been using it since I don't know when. So it's not, I mean, yeah. They didn't do what we did in order to stop the number of, to find the number of inner iterations. But the idea of replacing Tikhonov with this dynamic regularization in the nonlinear context has been there for a long time in the oil industry. So we're looking at an objective function now with many data sets. So it's big F, and this is big D, okay, where all the little f's are here and all the little d's are here in the matrix big D. And now we are looking at it at the Gauss-Newton iteration. So we have a matrix big W, okay, which has we draw S sub k vectors, yeah, from our, let's say, Gaussian distribution. And we estimate phi by this unbiased estimator, 1 over S sub k, what we had before, okay? But now you see the ones that we drew here, they come in and we have to define, so we had what we had the sources times W's times coefficients. And so we have, that affects also the Jacobian matrix of these Fi's, okay? And so you have here some, yeah, here I have a little problem of notation. This I was called J until now, but I cannot say J hat sub J, that's too much. So I called it I. So some of those Jacobians for the weighted sources, for the different weighted sources. Okay. So you see the Gauss-Newton method, the stabilized Gauss-Newton method is, in addition, modified by the stochastic method. And in fact, this is something that we did that we think is new, and the paper appeared only in 2014, that you're really using the Monte Carlo approximation 3 times. One, to calculate this delta M. The other one is to verify somehow that the current sample is representative. I mean, is it big enough? Can we reduce it? No. We try to only increase it, but not too fast. And then to assess the stopping rule. We need also phi for that. And if you're still with me, then here is the algorithm. And let me go through it. So we start with knowing what the sources are, and we start with knowing what the data are, okay? Different data sets, S of them, not S of them. The data are given. And we assume that we have rho and an initial guess for M. And you can use kappa equal 1 here. And then we initialize and set the number of experiments that we use to be 1, okay, just 1. We're going to grow it as needed, okay? And then we draw this matrix of S sub S times S sub k and do a Gauss-Newton iteration, and stabilize modified Gauss-Newton iteration. And then to check whether this is good enough, we draw 3 more matrices of sizes n sub c, n sub u, and n sub t. And then a cross-validation step. We check whether based on this, the C here stands for control. This is a control group. The unbiased estimator with respect to the control group, does it actually decrease when you move from m sub k to mk plus 1? And if not, then we say, oh, the size of the sample is too small. Increase it by a factor of 2. If yes, continue and see whether we can terminate. I'm sorry, yeah. Where am I? No. So if yes, then we do an uncertainty check. Sorry about that. So we are now assuming that phi hat at mk plus 1 is smaller than phi hat at mk based on the control group. And so now we look at this another group, another drawing of n sub u vectors, and we check whether the unbiased estimator is less than or equal than the tolerance. If it is, we look also at another group, another set, and if both of them are below rho, we say we stop. Okay. Otherwise, if they do not agree, then we merely iterate, but we do not decrease the sample size. Okay, so there is some various sort of bells and whistles here. How are these n sub c, n sub u, and n sub t determined? And this is where theory hopefully come to help. It's a bit of a mess, but it is possible to figure out some sort of value. So given epsilon and deltas, you can come up with the values based on those theorems that I showed you. I'm going to skip that. It's in the paper. And that allows treating the stopping criteria probabilistically in the quantifiable way. Okay. Our paper appeared in a journal of uncertainty quantification. Okay. So, but to understand it better, that's more important really. Let's say that we have a condition that says phi should be less than rho. Okay, that's what we are after at the end. And now we have an unbiased estimator based on n sub t drawing of random vectors. And suppose that we figure that it's less than or equal to 1 minus epsilon rho, or that it's less than or equal than 1 plus epsilon rho. What does it mean? Okay, that means that if this holds, if our test here holds, then with a probability of at least 1 minus delta, we got our stopping criterion holds. If this holds, if this does not hold, then with a probability of at least 1 minus delta, this does not hold either. This is the nature of probabilistic bounds. And so here we can connect. The rho is the given tolerance here, and how much uncertain we are in of the value of this rho. This is reflected by just choosing the delta here. Okay. Whereas the probability of false positive negative, meaning this one holds but this one does not hold, or this one does not hold and yet this one does hold. Yeah. That probability is controlled by the epsilon. It's a different world, and it takes time to get used to it, I know. It's also 5:20, I think. I know that. No, only 5:15, I have time. I know that too, okay? But there's something exciting here, really, and also something limiting that I will explain in a minute. I'm going to show you some experiments quickly. Maybe I'll show you that first and then come back to the point I wanted to make. So again, for this application here, and with these delta function sort of sources, okay. Vanilla here stands for don't do anything stochastic, just do the whole thing. You know, if you have 49 PDEs, all 49 PDEs, don't play games, okay? And so the vanilla with 49 sources ends up costing about 5,700 PDE solves. If you have 4,000 sources, then vanilla takes about 500,000. 500,000 is a bit too much. Okay. These experiments were done by Fred setting up the computer and going on vacation for a weekend or something and coming back to see if the computer stopped working. That's not, yeah. So on the other hand, if you use a Gaussian probability distribution here, you get this result with a comparable price as the vanilla for 49. Okay. Now, the results for the Gaussian, this is the least using what I described, namely the dynamic regularization. So this is the true model again, and it has a constant background of 0.1, and this body has constant conductivity of value 1, and this one is value 0.01. And this is a pretty good picture of approximation of the true model. This one is not. This one has all kinds of artifacts that if you did not see it, you wouldn't say necessarily that this is the correct solution. Okay. So you really do have better results. The point is, however, that the price has not increased. You actually get better results without increasing the price of the calculation. And here, we added total variation, again, well known and done by many. Total variation, and the results are, the costs are similar. Actually, they're even lower because the convergence is a bit faster. For the Gaussian, but similar. And here the results are much crisper than here because we are using more information. Here we're using a priori information that a true solution has jumps, discontinuities. Okay, and that is something that actually piecewise constant solution is something the total variation tends to produce. And that's what you see here. These results are very sharp, really, for such a diffusive problem. On the other hand, something that is not so obvious ahead of time is that the results with 49 sources is actually worse than what it was before. And so you introduce total variation because it's an a priori information, good a priori information, and you get worse results. That can happen with total variation. The essential reason, intuitively, is that 49 sources is not sufficient to capture the essence of the situation. And then the desire to make it more, more piecewise constant produces messy results. Something that you have to get used to. If you take here's another little secret with total variation. If you take a problem and you perturb the location of resources or something like that, and you do it a few times, okay, and you measure the variance. So you get a bunch of reconstructions, you measure the variance. With total variation, the variance will be larger than with L2 of the gradient. Okay. Almost done?
If you take vanilla with 4,000 and you introduce TV, what would happen then?
Oh, I did.
First?
So this is the TV with 4,000, with this many. Oh, sorry. If you do vanilla, then it's similar.
It's better.
Oh, yeah. So 4,000 already captures the problem, and then you say, oh, I have more information, then I'm going to use this successfully, the information that is piecewise constant. But if in some sense you don't have enough sources, then it's not clear that you're going to get better results just by using that. But it's not just any a priori, it is a very special way. It will not happen when you do multi-level sets. It will not happen. The level set takes much more advantage of the knowledge that you have here, a piecewise constant model.
But again, it's a priori information.
It is, yes, but it is a stronger. In the level set, it's a stronger a priori. The total variation tends to flatten, but it only tends to flatten the solution, yeah? And it does not penalize discontinuities as badly as L2. Level set says all I know is the solution is of this form, and so it's a much stronger prior. I wanted to say one more thing before. Yeah, I'm almost done. Almost done. One more thing. I'm not trying to sell anything here, even though I'm talking about my work, because I know it. So let me tell you why one reason why I'm less excited, and that is that the major thing, which is the S sub k, we don't use all this beautiful uncertainty quantification for that, because you want to grow it. There is some theorem that says that in the limit it should be everything in some way for theoretical bound. So the most important size n is, in fact, we don't use the uncertainty quantification for it. Conclusions, and I'm done. The thing that I wanted to emphasize out of this conclusion, the rest of them you can read at your own time because it's going to be available on the internet, is this. Bad combination of words. I strongly believe that this sort of results depend on the application. And so the results you saw are genuine and good, and I'm pretty sure that for electromagnetic experiments of a similar sort, with frequencies not too high, you get also excellent results. But what will happen for a problem which is sufficiently different, it's a different story. I think that, more applications are important here in order to study, because you have to look at so many parameters and how they play each other. More questions?
Could you use this also for the tomographic reconstructions? I mean, to stop the iterations there, because also there it's not always so clear when to stop.
I was actually thinking about it when you talked.
Yeah.
But I need a little bit more time.
Yes.
I
Okay.
haven't looked at it. That is the correct
Excellent.
answer.
Hopefully it can be used because it looks so promising.
Yeah. Thank you.